Thank you, viewers, and welcome to this lesson of today. I'm Mr. Dingo, and I want to welcome you so that you can continue learning about covalent bonds. In our previous lesson, we were able to talk about how covalent bonds actually form. And in that process, we talked about two main things. Let me say three main things. We were able to discuss the pi bonds and the sigma bonds, especially across single, double, and triple covalent bonds. And we also went ahead to talk about what we call bond lengths compared to bond strengths. Now, today we want to move forward to talk about what we call electronegativity of this particular covalent bonds. Now, as I've explained, as I've written here, electronegativity is the ability of an atom to attract a bonding pair of electrons. Now, that definition is actually very simple, but let us try to talk about two atoms here, chlorine atoms forming a bond. Chlorine atoms forming a bond here. We know that chlorine atoms forming a bond will be this way. If I try just to sketch the diagram, how it will appear. So this particular bond here, we know that chlorine atom and chlorine atom, they are identical atoms. So the attraction they are going to offer to this bonding pair, we have talked about the ability of an atom to attract. The attraction they are going to offer, each of this nuclear will offer to this one, and this nuclear will offer here, will actually be equal in strength because these atoms are the same. So it means that if you view electron density of a chlorine molecule, you are going to see a fairly uniform electron density. So we are going to have something like this forming. You are going to see electron densities because we know that the first energy shell is not shared, the second energy shell is not shared, but the third energy shell is shared. So you are going to have a diagram this way that try to show this is what electron density will show us. So electron density will be kind of fairly uniform, or let me say symmetrical. If you divide it into two, you can actually get two shapes that are actually very identical because these atoms here offer equal force or equal force of attraction to attract the pair of electrons that are in this particular point here. This point here, we know it will going to attract a higher electron density here. That's why you see it's much more broader here. So what we are talking about here is that if you have atoms with equal electronegativity, in this case we talk about electronegativity, the attraction, this one pulls the electrons here, and this one also pulls it to this other, is equal. If you have that particular elements, especially if you can only get that if you have elements, atoms of the same element, bonding like chlorine and chlorine form a chlorine molecule, we are going to form what we call a pure covalent bond. Pure covalent bond. Or sometimes we say normal covalent bond. So this normal covalent bond, like we are talking about here, results when you have atoms with equal electronegativities bonding together. And I said when you have such particular case, you are going to have electron density which is purely symmetrical. Symmetry. If you do some math, you will be able actually to understand what symmetry is actually. That when you cut this one into two and you fold this part here, you are going to find actually one shape that seems not to be added on another. It will be like you did not put one on another. If you cut it in the center, fold it and put it here, you will find the same one shape that will not be simply showing you different kind of shapes protruding or extending outwards. That's what we call symmetrical. But I said that only occurs if you have atoms with equal electronegativities. The force that they offer, or the attraction they offer to the pair, the electrons here, is equal. So electron density will therefore have an even distribution. What about if you have what we call asymmetric, not symmetrical but asymmetrical, meaning not symmetrical. If you have hydrogen, for example, hydrogen bonding with chlorine, hydrogen bonding with chlorine, what will happen? We know that chlorine is much bigger, and a chlorine atom in the nucleus, it has very many protons, 17. But in hydrogen, we only have one proton in the nucleus here. So this one here will create what we call a symmetrical electron density, because it means that this one here, the hydrogen is much more attracted the other side with these electrons than chlorine is pulled here, because electrons has very low electronegativity. It cannot attract because it has only one proton here, so it cannot attract this bonded electrons here towards itself so much. But chlorine can, because there are 17 positive charges here, which can actually has a lot of influence on the shared pair of electrons at this particular point here. So when we draw electron contours, we can simply say that for electron contour of hydrogen, if this is hydrogen, we are going to have something like this. We know that chlorine having like 17 electrons, we are going to have something like this. Then we are going to have something like that. So viewers, you see this electron contour of hydrogen, chlorine. This electron contour of chlorine. It will be the same electron contour with oxygen, hydrogen, and so on. It will be symmetrical. But you realize that this one here is asymmetrical. If you cut this shape into two, you try to fold it, you are not going to find one identical shape, because this shape here will be appearing in the center here, which will appear now. So this is not symmetrical, or what we can say asymmetrical. Asymmetrical. Why is it asymmetrical? It's asymmetrical because chlorine seems to pull the bonded pair of electrons here with a lot of force than hydrogen can. That is due to because that this one has more protons here, so it can pull these electrons with a lot of force than hydrogen can. Now, a compound like this is not purely covalent. It is what we normally form, we call polar bonds. Polar bonds are those bonds that actually you realize that if you dissolve hydrogen chloride in water, it will dissolve. But when you dissolve hydrogen chloride in water, it will dissolve because actually is very highly polar. Highly polar, we can show polar bonds, polar covalent bonds like chlorine here, with simply an arrow in between. When you find a bond written this way, then an arrow here, this one shows you that these bonds are polar. Sometimes we can show that because chlorine here is not purely positive, purely negative I mean, and this one is not purely positive because of the force here is much more greater, pulling, having influence. So we can talk about this one partially negative bond and this one partially positive bond here. So you realize that this kind of effect here, you are going to see it in very many substances like oxygen and hydrogen in water. We are hydrogen and fluorine. We are going to find that they are all polar in nature. Polar in nature because one atom is more electronegative than the other atom, because electronegativities are not the same. So it means that when you talk about this particular covalent bonds range between a continuum of polarity here. When you talk about one being purely covalent and another one being almost purely ionic. So if I talk about purely ionic here, 100% purely ionic, 100% ionic, or let me say purely covalent, let me start with that. Covalent, and then the other side we have purely ionic, meaning it is 100% ionic. So we are going to realize that the polar bonds here, the polar bonds we are talking about will be somewhere in between. They will be somewhere in between, depending on the electronegativity of the one atom to the other. So some may be almost closer the other side, some will be closer here. But the ones that are purely covalent here, we have said, they are those ones whose electronegativities are equal. For example, if you have atoms of the same element bonding, then you expect that their electronegativities are equal and therefore they form purely covalent bonds. But when you have what we call purely ionic the other side, we know ionic bonds what they are. So something that is much more closer to them the other side, it means that one atom is extremely electronegative than the other atom that is bonded with. That one moves worse. So that's why I talk about is actually ranging here. And in every here we have what we call polar covalent bonds. In between from 0 here to 100 pure the other side. In between here we have polar covalent bonds. And I've said polar covalent bonds, they arise as a result of one atom being more electronegative than the other atom, and therefore it tries to cause what we call partially positively charged and partially negatively charges, and that is why these substances, when you dissolve them in water and actually they dissolve, they actually conduct electricity because they are free ions that actually exist. But when you come purely covalent compounds do not have that particular behavior. So viewers, that's as far as electronegativity is concerned. Please read and be able to help us deal with these cases. In your examinations, the electronegativities of different elements in the periodic, across the periodic table will be provided for you in the booklet for formulas or data or other information you need for your mathematical aspects of chemistry. So don't worry about electronegativities. When you have electronegativity in the table, if you are asked whether something will be polar or not polar, just look at the electronegativity of those two atoms together. Then if they are equal, you know it's purely covalent. If they are not equal, you know it will result to a polar covalent bond. Thank you, viewers, and I want to urge you to subscribe to our channel so that you can support us in this endeavor of teaching people during this time of corona crisis. We regret that children have to be at home and the syllabus is going on, but life and health comes first. So encourage your children to stay at home to be safe so that they can learn while at the house, because we are here for them. We are here to support them, and the only thing we ask from you is to be able to subscribe to our channel, and that is all. Thank you very much, and see you next time when we look at other aspects or other parts of covalent